Thank you, Josie. Well, it's my great pleasure to welcome my friend and colleague, Tom Rippeth, who is Professor of Oceanography at the University of Bangor in North Wales, of the United Kingdom, formerly the European Union. So Tom comes from Newcastle in the northeast of England. He did his bachelor's degree in physics and meteorology from Reading University, not far from London, and then did his master's and PhD in physical oceanography at the University College in North Wales, now Bangor University, and his supervisor there was John Simpson, who's on the Zoom meeting today. So welcome to you as well, John. Tom was a fellow of the UK Natural Environmental Research Council as an independent research fellow. I like that word, independent, for 8 years, and then he came to the academic staff and worked his way up to full professor of physical oceanography at Bangor. Are you the head of the school, Tom?
No, it's a sort of a symbolic post. You get the of. There are actually two other professors in physical oceanography as well. It just, I suppose, it shows I've been around longer than them.
Well, that's good news that you're not head, so you can do something.
Yeah.
The title of Tom's talk today is interesting, very interesting. It's called The Atlantification of the Arctic Ocean and Its Impacts. That's a new word, Atlantification. So Tom, I'll hand it over to you and I'm muting.
Okay, thanks very much. So this picture on the front, John Simpson and Kamazima, who I think we shared a house, didn't we, when I was doing my PhD and you were doing yours in Menai Bridge. This is the Marine Science Laboratories, looking out over the Menai Straits, as some of you might have read papers about, with the Menai Bridge, with the Menai Suspension Bridge in the background, and the pier in the front is where we have our research vessel sail from. And the reason I show this is it's because it was during a very severe winter that we had about 10 years ago, when we had not only snow on the ground, but actually very low temperatures, which is really unusual for the UK for long periods, because our weather's normally dominated by westerly winds, which bring us warmth from the Atlantic. So the Gulf Stream gives us a relatively mild winter and also a relatively wet winter compared to other areas. But this particular winter was very different because the weather was actually dominated by polar air masses moving in over the UK and sitting there for weeks on end, resulting in very extreme temperatures. So it looked a bit like the Arctic. It's not the Arctic, but as we get to the end of the talk, I'll hopefully show you some of the links between that very cold winter we had back in 2010, 2011, and what's going on in the Arctic Ocean. So we've been working up in the Arctic. I think the first foray there was about 2007 from Bangor, and the main collaborators in Bangor are shown here on the screen. So we have two people who both came to Bangor as postdocs, became independent research fellows, and are now faculty members. Young Jean-Len. So Young is a Scripps PhD graduate and a Cambridge physics graduate, who is now a reader in physical oceanography. She's also an editor of JPO, so she's somebody you have to keep on the right side of. Matthias Green, who originally did his PhD with somebody who is a close friend of ours, Anders Stigerbrandt in Göteborg, and he is now a professor of physical oceanography in Menai Bridge as well. And they've both been involved in the Arctic work, and they've both recently published a very exciting popular science book called The 32nd Ocean. So if you have any relatives that are asking you about how the ocean works, this is the book for them, because it really is popular science. And then we have the two Bens, so Ben Lincoln and Ben Powell. They've done most of the observations. The picture shows them claiming a bit of the Arctic ice pack for Wales. Unfortunately, it melted, so Wales's interest in the Arctic has disappeared temporarily. And aside from the Bangor team, we have a large team of collaborators from the UK, from places like UCL, Oxford, National Oceanography Centre. From elsewhere in Europe, we've got Bergen, we've got the Norwegian Polar Institute, we've got collaborators in Germany and France and Canada, and also collaborators in the US, in Yale University and in the University of Alaska at Fairbanks. So they all have participated in different elements of this work. So the Arctic is probably one of those places. When I was in school, we used to have a map of the world, and there was just a white band across the top, and it was never really talked about. And when I was first starting to do oceanography, probably for the first decade or decade and a half, we didn't hear a lot about it because access was very difficult, partly because it was totally encrusted in sea ice for pretty much all of the year. So there weren't really the opportunities for observations that there are these days. But also, I guess, partly because of the Cold War, meaning that large parts of the Arctic were inaccessible, something which is sadly happening again today. But it really sprung into prominence probably about the middle of the 2000s, because people noticed that the sea ice extent in the Arctic was diminishing rather rapidly. Now, there's a seasonal cycle in the Arctic and sea ice. It's a maximum about now, at the end of the winter, as the sun rises from 6 months of darkness, and it melts away to a minimum in about September. And in this map, you can see the Arctic Ocean. It's connected to the North Atlantic through the Fram Strait down here. This is Norway, this is Greenland. And then you've got a little strait, the Bering Strait, which is almost estuarine in nature. It's only about 50 meters deep between Alaska and Russia. And then you have these large shelf systems. So most of the Arctic Ocean is actually a continental shelf sea. And then the deep basin here going down to 4,000 meters. And one thing to note about the Arctic is it's probably the ultimate in ROFE's regions of freshwater influence, because though it only represents 1% of the ocean's volume, it receives 10% of the fresh water through these huge river systems, particularly the Russian river systems, the Lena, the Ob, the Ensi, etc. Now, the sea ice in the Arctic, the mean or the median ice edge between 1981 and 2010 was something like this. So you can see there was no chance of getting through the Northwest Passage, and there was very little chance of getting through the Northeast Passage. But by 2020, that ice edge during the September minimum had really gone back, and it exposing for the first time large areas of the deep ocean basins to open water conditions. So previously, the ice edge always sort of stopped somewhere in the middle of the continental shelf seas in the minimum, whereas by 2020 it's really pushed back. And people were sufficiently concerned about this by the mid-2000s that they were worrying that the Arctic Ocean was actually reaching some sort of tipping point, whereby the ice was going to accelerate really rapidly and disappear. And I think there was one UK scientist who I won't mention, but had nothing to do with Bangor University, who predicted that all of the sea ice would disappear in the summer by 2015. Well, he was wrong. And it's questionable whether it will disappear within our lifetimes, I think, because of what I'm going to talk about now. But this whole idea of a tipping point has to be predicated on what's happening in the ocean. Because if you have the atmosphere, okay, you can warm the atmosphere in the summer, and it can get warmer because of the greenhouse effect in the summer. You put the heat into the ocean, it goes back into the atmosphere. But at some point in the winter, all of the heat's gone and the ice will come back, because basically in the winter, your radiation balance is all in one direction. You're losing heat to space. You're not putting anything in apart from convection, essentially by winds, unless, of course, the ocean is having an influence in importing heat to the Arctic region. So over the last decade and a half, what we've seen is this big decline in seasonal sea ice. So we've gone back to 79 here. We can see probably up to 96, maybe even 2000. The sea ice minimum was just oscillating around an average of about 9 million square kilometers. But more recently, there's been this longer term decline with extreme minimums reached in 2007, 2012, then again in 2020. Now these are actually the October values shown here. If we look at the September values, we can see what that means in terms of the aerial coverage. We've gone from having pretty much all of the Arctic covered in snow and ice. And of course, snow and ice is very shiny. It's like a big mirror. So it's just reflecting the sun's rays back to space. So you might be pumping the solar radiation in for 24 hours a day because the sun never sets at those latitudes, but it's just being predominantly reflected back to space. But by 2012, you can see huge areas of open water. In the summer, they're absorbing the solar radiation. That then gets re-emitted to the atmosphere as infrared radiation, and it causes the atmosphere to warm through the greenhouse effect, even apart from the fact that greenhouse gases are rising. So this is a warming effect that doesn't even require greenhouse gases to rise. It would happen anyway. And this is a process that's called Arctic amplification. And the concern is that involved in this process is a positive feedback mechanisms, which could accelerate this whole process. So the story in the Arctic really starts with this chap here, a guy called Fridtjof Nansen. He was an oceanographer based in what was called Kristiansand at the time. He was then went on to become an ambassador for what was the predecessor of the United Nations. And he had the job at the end of the First World War of settling all the dispossessed people. People have basically lost their nations when they redraw the boundaries through something called the Nansen Passports. And he was awarded the Nobel Peace Prize for that work. So if you compare him to a lot of modern day politicians, the Trumps, the Boris Johnsons, all of these guys, you would put probably Nansen very high up and those guys very low down for comparison. But of course, Nansen was an oceanographer, and we shouldn't forget what he achieved as an oceanographer. And he was also a great explorer. When he was waiting for his PhD result, he actually skied across the heart of Greenland, and they were the first explorers to do that, to discover there was this massive ice sheet covering Greenland. And being an oceanographer, he knew that the ocean was actually circulating under the ice in the Arctic. And he had this idea of becoming the first person to get to the North Pole by building a ship that could be frozen into the ice and could drift with the ocean currents and take him to the North Pole. And this is the ship, the Fram, which was designed. It had a wooden hull, and the wooden hull was curved like this. So when the ice formed around it, it just lifted it out of the water. So it kept it nice and safe, not like the British ships that were getting crushed in the southern hemisphere by the sea ice. And basically the explorers could live on the ship and they could travel to the North Pole. And at the time, they weren't just going to travel to the North Pole, but they were going to make the first scientific measurements in the Arctic as they went. And Nansen made some really important measurements. The first one was actually the depth of the Arctic Ocean, because at the time they didn't realize there was a deep basin of 4,000 meters, so similar depths to the Atlantic Ocean in the center of the Arctic. They thought it was just a cold, shallow sea, but Nansen discovered there was actually a very deep basin. And through using these bottles that he designed, Nansen bottles, lowering them down on wires, sending messengers down, which caused them to close, trapping some water, breaking the mercury in thermometers, he was able to make the first profile of temperature and salinity in the Arctic Ocean. And this was one of the first. This was made over a 4-day period. You can imagine sending these bottles down, hauling them back up virtually by hand, sending them down again is quite a time-consuming occupation. So it took them 4 days to make this 4,000 meter profile. We compare that to today with an electronic CTD, when we would probably make the same sort of profile in about 3 or 4 hours. And what he discovered was, yes, the surface water was very cold, very close to the freezing point of seawater, so -1 degree, 5 degrees Celsius here. But as he went down, it warmed, and you got to about 200 meters, and you saw there was actually a temperature maximum. It was about ½ a degree at the time he was there. And you had this warm layer of warmer water, and it was also saltier water. So although it was warmer, it was actually heavier than the water close to the surface. So it was residing at this intermediate depth. And this warm, salty water had to come from somewhere. And Nansen, understanding about oceanography and having read up about how the early ideas about how the Arctic Ocean circulation worked, surmised, as it turns out correctly, that it was essentially part of the Gulf Stream current system, the bit that breaks off, goes up the Norwegian coast, and then it's entering into the Arctic Ocean, bringing this warm water this heat with it into the Arctic. And we got a profile in 2018, probably about 40 kilometers from the original profile of Nansen's. And you can actually see in this same location, this Eastern Arctic location, Nansen's profile here is black dots. And then the blue line is actually the profile taken in August 2018, so taken about 3.5 years ago. And you can see that this warm water that's coming into the Arctic has actually warmed quite considerably since Nansen was there. So it's about 0.5 degrees Celsius, and it's now about 1.5 degrees Celsius. So there's been significant warming, but also that the warmer water is actually closer to the surface at this location than other locations than it was when Nansen was there. So it could be there's just some variation in the temperature and variation in the height of the water, and Nansen just happened to be there when cold water was there. We happened to be there making this measurement when warmer water was there. So that's one of the questions that we need to answer. So the reason that we got involved in the Arctic is because we're interested in mixing and turbulence, stirring temperature gradients, and fluxing heat. And guys who were putting together the first proposal, which was for the year of the Arctic, about in 2007, 2006, 2007, were interested in whether we could make measurements to see how fast this Atlantic water was getting up through this cold halocline. So all this very cold fresh water that sits above it, how quickly it's getting up to the surface, and therefore how quickly it's nibbling away at the bottom of the sea ice. Because of course, if you've got heat being mixed up, then from the ocean, that heat could be being mixed up all year round. There's nothing to say it can only happen in the summer or the winter as far as we understand. So it's not like the atmosphere, which is only doing the warming in the summer. So if you're talking about tipping points and feedback mechanisms, the ocean has a stronger potential through this mixing mechanism if such a mixing mechanism occurs, which allows this heat that Nansen discovered to actually get to the surface and melt the ice, because there's enough, or there was estimated to be enough heat back in 2010 to melt this ice 2 or 3 times over. So there's probably even more now. So we made our first measurements in 2007 in the Eastern Eurasian Basin. So the measurements at Nansen and the comparable measurements I showed you were made about here on the end of this red line. And there were 3 series of measurements made. They were made using a turbulent microstructure profiler. So they're telling you about the rate at which turbulence is dissipating. And therefore, heat fluxes could be calculated. So the red was in the western part, the green in the middle, and then the blue in the east. And these were the first profiles that we took. And you can see that as you move from the west to the east, which is the direction of the prevailing circulation, the water gets cooler, and you can't quite see it here, but it also gets fresher. And one of the key points is that these profiles aren't straight, they're actually stepped. And that's telling us something very important about the nature of the vertical exchange processes occurring there. It's telling us that you've got something called double diffusive convection going on. Okay, and that occurs when basically the exchange is driven by molecular diffusion. And it occurs because salt and heat diffuse at very different rates. So if molecular diffusion is dominating exchange here, it's telling us that there's no turbulence. And our turbulence profile measurements actually told us that there wasn't any turbulence. So we were the first people to make turbulent measurements in this part of the Arctic Ocean, and we found there wasn't any turbulence, which could be regarded as something of an unexciting result, but we persisted. And we published this paper here. And in the paper, Young, who was the lead author, was able to show that basically the heat fluxes that we observed couldn't explain the rate at which we were seeing the water cooling. Okay, because we got the heat fluxes from knowing that what the heat fluxes are in double diffusive staircases, and we couldn't explain the changes that were taking place here. So they could have been just because the water mass properties are changing sufficiently in the inflowing water between that by the time the water travels from here to here, you're getting changes anyway. or it could be that there's some sort of intermittent mixing processes taking place which are responsible or dominating these changes. So jumping ahead a little, so Young with a PhD student, Ben Barton, we're actually interested in using satellite data to try and plot the flux of heat into the Arctic. And the region they focused on was actually this region, the Barents Sea here. So up until now, we've been talking about this region here, north of the Rippeth Sea, but we've gone to the Barents Sea. And this is the region where the Atlantic water first flows into the Arctic Ocean. And what they were interested in looking at were how the seasonal sea ice in this region's changed. So this plot here basically shows you the sea ice extent by latitude in time. So starting in 1985 and going through to 2017. Okay, and what you can see in the northern Barents Sea, certainly for the first few decades of the measurements, is you had sea ice all year round. So this region here around Svalbard and that area, you had sea ice all year around. But then in the southern Barents Sea, so down here, what you see is that you had ice in the winter, going right down to 72, pretty much every winter, and then that melts back in the summer. So you had seasonal sea ice. But what's happened since about 2005, 2006, is essentially the seasonal sea ice has disappeared in the southern Barents Sea, so this region here, and the sea ice is becoming seasonal right up to 82 degrees north in the northern Barents Sea and moving off the shelf break region here. So that there's been what we could call a regime shift in sea ice in the Barents Sea region here. And when they've compared that to the temperature of the Atlantic water in the Fram Strait, so flowing into the Barents Sea, you can see that this temperature does actually vary by about a degree or two on periods of several years. But you get to 2005, 2006, and there's a big jump. Okay, so the minimums are now starting to match the previous maximums, and the maximums are probably about a degree warmer than they were before. So what we've seen in this region of the Arctic here, around about this time that we were starting to make our measurements in the Eurasian Basin, is a big jump in the temperature of the Atlantic water, which is flowing into the Arctic Ocean. And that has had a severe influence on the sea ice extent in the Barents Sea. So I'm guessing this is the first evidence, or the earliest evidence of the Atlantification taking place. It wasn't the first published evidence, it was the earliest evidence, I should emphasize. And the Atlantification, the increasing influence of the Atlantic water, was actually happening here in the Barents Sea, and it was very clear because the influence was on sea ice extent, which was something that we can observe all year round using satellites, which is what these guys did. Now moving to the eastern Eurasian Basin, so the bit where the measurements were first made by Nansen and the bit where we're making them, you can actually see, so this is a time series, this goes from 2000 to about 2018. So this is a huge project which Igor Polyakov at the University of Fairbanks, Alaska has run. Hugely insightful to decide to make measurements in this region, as we'll see as we go on. And they've maintained moorings there pretty much consistently from 2003 through to 2018. And we were hoping to be extending that, but I'm not quite sure how things are going to work out with that in the future. And you can see here two lines. You've got the Eastern Eurasian Basin. This is the mean temperature, 250 meters, so the core of the Atlantic water. And then we've got the temperature in the Fram Strait. Okay, and you can see the temperature in the Fram Strait. There's a much stronger seasonal cycle. It goes up and down. So this rise here is the one corresponds to the big one that Young et al. were seeing. And you can see that even in the Eurasian Basin, there's some temperature variability, which appears to be correlated with a lag of about 2 years with what's happening in the Fram Strait. So we are seeing some variation in the temperature year in, year out, which might explain some of the variability we saw in our initial measurements. But we are seeing some very warm temperatures penetrating right into the eastern Eurasian basin. So if you think back to the early 2000s, we were talking about temperatures between about -2 and 0. We're now up to 2 degrees and only dropping to just below 0. And at the same time, the halocline layer, so the layer of fresher water, has hugely shoaled. And that was something that really started to happen 2016, 2017. So it does appear that the conditions are changing in the Eastern Eurasian Basin because the Atlantic water is getting closer to the surface and it's also getting warmer. Now, unfortunately, we didn't have any turbulence measurements over that period. But what we can do is we can look at how conditions have changed and we can infer how turbulence might have changed. Now, we've got 3 plots here. The top one shows you the stratification of the upper ocean, basically. And you can see that the annual average stratification has declined and the summer values in particular have declined. So the upper ocean stratification has weakened over this period, 2003 to 2018. We have the upper ocean currents here, and these are in the diurnal inertial bands. They could be the tides, it could be due to wind or whatever. And there's the annual average, and there is the summer average. And we've also got the shear, which is are the blue measurements. And we can see that the currents do seem to be increasing, and in particular in the summer, but also the shear over the upper ocean is increasing. Now, if we work out the ratio of stratification for shear, if that decreases, that's telling us we're moving towards a regime where we're much more likely to see turbulence being triggered and therefore much stronger mixing taking place. And we can actually see the ratio here, which we've called the Richardson number, which is essentially a proxy for mixing, shows a significant decrease in both the annual, but also in particular the summer ratio of stratification and shear. So it looks like there's actually more mixing taking place along with the same time period as we're seeing this warming water coming in. And by doing some correlations between the shear, we can see that the shear is increasingly negatively correlated with the ice concentration. So the less ice there is, the more shear we see. It's increasingly correlated with wind speed. So you're taking the ice away, but also the windier it gets, the more shear you're getting. And what this is suggesting is that we're getting an increased coupling between the wind and currents due to the absence of ice, which could be a new positive feedback mechanism. So basically, we're getting more heat pulled towards the surface, mixed up towards the surface, and there's less ice, which is promoting more shear, which is promoting more mixing, which is bringing more heat up. So this could be a positive mixing mechanism. But if we go elsewhere in the Arctic, so our third opportunity to go to the Arctic was actually with the Canadians, and we went over to the Canada Basin. So we're in the Western Arctic now, and we went in 2012, which you might remember was the lowest sea ice extent ever measured on record. And not only that, but the cruise actually took place during the worst or the most intense Arctic cyclone ever measured in summer. Okay, so we were making turbulence measurements in this region of the Arctic, the Canada Basin, during the biggest Arctic storm that had ever occurred in summer. And what we found was, these are profiles before and after the storm, that when you get down to the level of the Atlantic water, so in the Canada Basin, you actually get a layer of Pacific water, and the Atlantic water is a little bit deeper. And when you get down to this layer, what you could see was that these staircases that we'd observed in the Eurasian Basin, they were preserved throughout the storm, which is making us think there probably wasn't any turbulence even associated with the storm. And then when we come to measure the turbulence, we saw that basically the level of turbulent dissipation that was occurring was virtually the noise level of the instrument. So we weren't actually getting any enhanced turbulence except over the sloping regions where there was a little bit of enhancement. So what we think is happening here is that despite the open water conditions, despite the very strong wind mixing, the energy or the shear doesn't get down to the depths where it can actually cause any mixing. And the preservation of the staircases tends to back that up. So there's essentially too much stratification in the Canada Basin for the wind to have any impact. So we're starting to see some sort of difference occurring between what's happening in the Eurasian Basin of the Arctic and the Canada Basin of the Arctic. Now, this enhancement of the dissipation over the slopes led us to think, well, maybe the tides were important. And coming from Bangor, I think Malcolm and Charles will be saying, yeah, tides are all the people ever talk about in Bangor. So we started off talking about the wind, but we're back on the tides again now. What we did was we combined all of our turbulent dissipation measurements, and the map on the right shows the Arctic. Each one of these green profiles is a measurement of turbulent dissipation. And if you put on where the seasonal sea ice is, you can see we've basically covered everywhere that it's possible to cover without seasonal sea ice with dissipation measurements. And what we've done is we've done transect averages along the transect. So you can see 6 there, you can see 7 here. And we've plotted them with latitude moving around the shelf break. And this is the dissipation, which is essentially measured, averaged over the Atlantic layer and the thermocline that sits above it. And you can see there's actually quite large variability as you move around the continental shelf break. But the variability isn't impacted by whether the measurements were made under open water or ice cover. So that's what these different shapes show. There's the conditions that we're making the measurements using our profiler, which is shown on the left here. And what we did was we compared that to the amount of work that the satellite measurements were telling us was being dissipated by the tide. So basically calculating the work done by the tide, the flux of energy into a particular segment of the ocean, and inferring the difference as being the dissipation. Okay, so using basically sea surface slope measurements here. And that's what this blue line shows. And it does show that the dissipation due to the tide over the continental slopes actually varies by several orders of magnitude, and it correlates quite nicely with the rates of dissipation that we're observing within the intermediate water depths of the Atlantic water. So this isn't due to tidal friction at the seabed. It must be something that's injecting tidal energy in the middle of the water column. And that created us with a bit of a problem, because what you would normally see in terms of tidal energy being injected in the middle of the water column is, as the tide flows over sloping topography, it generates something called an internal tide. Now, an internal tide essentially occurs when you've got a tide flowing over sloping topography, and to conserve mass above and below the thermocline gets pushed down as the tide flows off slope. Now, most of the Arctic is above what they call the critical latitude. And that means that any lee wave which is formed by the tide gets trapped on the topography. It can't propagate away because the tidal period is actually more than the local inertial period. So you've got this situation where the tidal flow will create a lee wave, but that lee wave is actually trapped on the topography. And that actually means that the efficiency of the transfer of energy from the tide, the barotropic tide, into the lee wave that then becomes the internal tide is actually relatively low compared to the mid latitudes. So we tried to explain this with some friends in Plymouth University, Vasily Vlasenko and Natalia, and they ran a very high resolution non-hydrostatic version of the Princeton Ocean model, and they ran it for the Spitsbergen Bank, which is just south of Svalbard, where we'd made some measurements, and these were the results. So what you see is you see the tide flowing over the bank, the tide reversing and flowing back over the bank, And you do see some sort of impact on the height of the isotherms. So the isotherms here are 0.5 degrees. And within these yellow zones, you're actually getting potential energy transfer from the barotropic tide into the whatever this internal tide thing is. So you're losing energy from the barotropic tide within these yellow zones. And what we've plotted here is quite a complicated diagram that shows the evolution through time. So this is time going up here, and this is distance over this slope. And you can see that the tide will actually push up the wave. So this yellow is the indentation we see here onto the bank. When you get onto the other side of the bank, the green line is showing that it's essentially trapped. It can't really escape, and then the tide changes and things move back. So you get this very non-linear situation with all these high frequency waves and things occurring there. And what you actually find is that the flow over this bank during most of the tidal cycle is supercritical. So there's an internal hydraulic control over this flow. And the supercriticality is actually shown by these colors here. So it's another one of these diagrams. This blue line shows the direction of the tidal flow. And the tide's about 30 centimeters a second. So it's relatively weak for a tide flowing off a shelf break, typical of quite a few bits of the Arctic. And you can see the wave fronts plotted as red and green. And you can see these periods here are periods where the flow is actually subject to this hydraulic control. And what that implies is that not only do we get some sort of energy conversion associated with injection of potential energy associated with the thermocline being pulled down, but you're also getting conversion, direct conversion, associated with the turbulence, associated with the internal hydraulic control of the flow. Okay, so that's where we think a lot of the dissipation takes place. And Vasily actually showed that 71% of the tidal conversion that we observed in this model was actually associated with this supercriticality. So although the conversion of potential energy to an internal tide is low, to a linear internal tide is low and is trapped by the topography, you're getting all of this extra energy which is being pumped into mixing by this hydraulic control. Now we did look to doing some measurements here, but unfortunately we didn't get funded, but one of our partners in Norway, Ilkefur, did. And he went and made a series of measurements a bit further north. So he's making measurements of turbulence actually north of Svalbard. And here, the tide is actually diurnal. So it's flowing across the slope. It's diurnal. And you've got a time series of measurements here, which is a 24-hour time series. You've got turbulent dissipation here. And the hot colors are it means there's lots of dissipation, so lots of mixing. And the cool colors mean there's not much. Then you've got the off-shelf flow here. So I think the intense colors show the off-shelf and the on-shelf flow. Then you've got the percentages of time that the first and second modes of the flow are hydraulically controlled. So the Froude number is bigger than 1. And then you've got here in blue, depth average dissipation, excluding the boundary layer, and the fraction of the water column where the Richardson number is less than 1, so where we would expect to see turbulent dissipation. And you can see here that you get some very intense flow actually around slack water. So the depth mean flow is close to 0, but you've got a strong on-slope flow in the surface near the bed and off-slope flow in the middle of the water column, and you've got very strong tidal dissipation taking place here. Okay, and it's basically the flow is being hydraulically controlled at this point, so you're getting shear instabilities and very high levels of mixing taking place. So the tide does appear to be an important contributor to mixing within the Arctic Ocean, but only over certain slopes. And it's due to a different mechanism to the mechanism we would normally expect to see linked to tidal mixing in the Atlantic Ocean. In other words, the generation of linear internal tides. Now, in this paper, Ilke actually estimated the heat flux arising from the tidal mixing in the Arctic Ocean due to this mechanism. And he found it to be comparable to the heat flux associated with the double diffusive convection, which is actually responsible for the heat fluxes over about 70% of the surface area of the basin of the Arctic Ocean. So the tide is only important over limited areas which are topographically controlled, but it's pumping a lot of heat up towards the surface. Now, we made measurements in 2018. So this was a project that Young was actually running with the guys at Fairbanks, Alaska, and also with partners at the Alfred Wegener Institute, including Kiki Schultz, who wrote this paper. Made measurements that were close to the ones that we started out talking about. So this is in the Eastern Eurasian Basin. Now, this is a region where there's not any great tidal flow. It's a region where the tidal conversion based on our satellite measurements is very low, but we found a profile, and this red profile of dissipation in this region here, which showed actually very high intermediate depth dissipation levels compared to the background we normally saw there. So this is a background. This is actually these are actually the profiles that we observed in 2018. And we found that it actually corresponded to a very strong downslope flow. A downslope flow is about 50 centimeters a second. So it appeared to match all of the criteria we need for the development of one of these unsteady lee waves. But in this case, the unsteady lee wave wasn't generated by the tide. It was actually generated by something called a continental shelf wave. Okay, and the continental shelf waves are just, I think, becoming recognized as being important contributors to the variance in the currents in the Arctic. And they arise because of storms that are occurring essentially at lower latitudes outside the Arctic or just inside the Barents Sea and over here in the sort of Chukchi Sea area. And they arise because a storm will either pile water up against the coast or push water away from the coast, and that will set up a disturbance which will then propagate eastwards around the Arctic Ocean. And Kiki actually focused on this location here, looking at sea level height information and estimate how many continental shelf waves had been between 2015 and 2018. And what she's done here is she's plotted it against sea ice extent over this region here. And you can see that there are very few continental shelf waves during periods in the winter where there's complete sea ice coverage. But as the sea ice disappears, you're getting more and more of these continental shelf waves, and by implication, big mixing events occurring in this location. So what we think is happening, and probably explains the first measurements by Young, is we are getting significant mixing occurring in this region here. And it's actually linked to continental shelf waves, which the propagation of which is linked to the presence of sea ice. So these continental shelf waves occur, you can see 4, 5, 6 times a year in seasonally sea ice free periods, and they drive significant amounts of mixing. So that could possibly answer the question that Young posed with those first ever measurements back in 2007 and 2008, and it provides a mechanism which is linked to far field weather conditions. So if you're getting more severe weather conditions here and here, you'll be getting more mixing taking place over the shelf break regions around here. And it's also linked to sea ice cover. So that's taken you a quick whiz about different mixing mechanisms in the Arctic Ocean. And if we come back to looking again at this region where there's this NABOS observing system that Igor Polyakov set up in 2003 and still runs, what we can do is we can talk about what the possible mixing events are. We can't link them as yet to the actual observations because we don't have direct observations of currents, but we can infer heat fluxes just by looking at the changes that are occurring. And what we find is that the average heat fluxes in the winter were about 2 or 3 watts per meter squared. So this corresponds to the measurements that Young made, but they've increased year on year. So the most recent years, they're in excess of 10 watts per meter squared, and that's 2017-18. And what they're equivalent to is basically the loss of about a meter of ice in the winter. So you're stopping ice forming in the winter, or you're stopping a meter of ice forming in the winter. And the heat fluxes have actually overtaken atmospheric heat fluxes for the first time in this region in causing warming. So we've got this potential warming mechanism, which appears to be linked to sea ice. Sea ice is declining, it's driving sea ice decline. So we've got this positive feedback that's going on. So my summary part one, so I didn't really talk about the continental shelves because I didn't have time, but there's an article which has just appeared this last week in Oceanography magazine, which covers that, which is free to download from their website. The key about mixing on the continental shelves, of course, is that helps set the upper ocean stratification through determining the conditions of the water which are flowing into the halocline. So we see mixing hotspots. They're due to both the wind, but also other subinertial barotropic flows. And some of these are linked to ice decline. And it's the unsteady lee wave mechanism, which is really important. So you can't just calculate the depression due to the lee wave to get how much energy is available for mixing. You need to also account for this internal hydraulic control process. And none of this is parameterized in the sort of climate simulations used in, for example, IPCC to predict future Arctic sea ice decline. And I think one of the things that we can say is that there are very different responses in the eastern and the western bases of the Arctic Ocean, with this new positive feedback mechanism in the eastern Arctic Basin. And what we're seeing is basically the changes in stratification are driving this positive feedback in the eastern Atlantic Basin, which is causing an increasing influence of the heat from the Atlantic water, in other words, Atlantification in that region. So all of the excitement really is happening in the eastern Atlantification, in the eastern Arctic Ocean, in terms of sea ice decline linked to oceanic heat. So you're probably thinking by now, why would people in North Wales be interested in what's happening in the Arctic? And what's that got to do with the snowy picture of Menard Bridge at the beginning? Well, we can go back to history, and one part of the Second World War that you probably haven't heard anything about was in a very extreme environment in this region here. So this is Longby Iron on the islands of Svalbard, and there was actually an ongoing battle went on here, which had lots of casualties, but not more to shooting, to things like frozen lungs, missing fingers, amputated legs because of frostbite, and all the rest of it. Because basically the battle there was more against the weather than the enemy. And the battle was because it was realized even at that time that what is happening weather-wise in the Arctic has an influence on mid-latitude weather conditions. So basically both the Allied forces and the German forces realized that by making weather observations that included observations in the far north, they could predict the weather sufficiently far in advance to plan things like, for example, the D-Day landing. So places like Svalbard actually became conflict zones because of the need to make weather measurements there. And it's that link, really, which gives us an interest in the UK, and I'm guessing you guys in the sort of the central bands of the US, an interest in what's going on in the Arctic. And it's all to do with something called the jet stream, which is a high altitude wind, and I'm sure most people in the audience know more about than I do. But it's a high altitude wind, and I know that it can be very strong because I've got on planes in New York, and the captain said, we're going to be in London a couple of hours early because we're going to sit in the jet stream that's blowing at about 200 miles an hour today. But it's also this, it also is the guide for storms across the UK and mainland Europe. And when, for example, we sit to the north of the jet stream in the winter, we get cold air incursions coming from the Arctic, so we get cold conditions. When we sit to the south of the jet stream in the summer, we get warm air conditions, so we get potentially warm heat waves, dry conditions. And if you get what are called blocking highs occurring, when basically the waves in the jet stream break, then you get weather conditions occurring for a long time. So you can have very severe weather conditions persisting for long periods in the winter, or very dry conditions persisting for long periods in the summer. And it's those severe weather conditions which are the thing that worry us in the UK as being the thing about climate change, which is going to have the biggest impact. And of course, the weather conditions associated with the jet stream are influenced by conditions in the far north of the Arctic. And there's an ongoing debate really about how much, in particular, the heat which is being released from the Barents Sea into the atmosphere, reducing the atmospheric pressure, is influencing the jet stream over the UK. And there's a big project which young Len in Bangor is involved with meteorologists at Exeter University and oceanographers at Oxford University to try and unpick that relationship. So I'll just end on pointing out what the most recent IPCC report concerning polar conditions is telling us. It's telling us that the polar regions are losing ice, their oceans are changing rapidly, and the consequences of this transition extend to the whole planet, but that we don't really have high confidence in the nature of the linkages between the changes in the Arctic and mid-latitude weather, because we don't have a full understanding of the complex interactions between physical processes. And my reading of the IPCC technical summary failed to see any mention of this idea of Atlantification, increasing influence of the Arctic Ocean. So that's probably a good place to stop.
Well, thank you, Tom, for this very eloquent and clear explanation of very complex mixing and transport processes in the Arctic. And you've been able to say this to a wide audience. So it's very interesting, and you need to get involved in the IPCC by the sounds of it. But let's have some questions from the audience. Everybody, here we go. Kamazima.
Yeah. Great, Tom. That was a great talk. And I want to go first, not to the physics. Let's go to the biology. You know, biology is more important than physics, right? How has this change in temperature, especially in the Barents Sea, changed the biogeography?
So there's a whole series of papers just been published in the Philosophical Transactions of the Royal Society about that, and I haven't read any of them because I haven't really been involved in any Barents Sea work. But if we go back to this region here, the main supply of nutrients, nitrate and phosphate, to the Arctic Ocean doesn't actually come through the rivers. It comes through the Atlantic and Pacific inflowing waters. So not only do they bring heat in, but they also bring nutrients in. So the mixing, particularly over the shelf break regions and the outer shelf regions, of nutrients upwards is key to supporting the food chain through supporting primary productivity. And in this Eastern Eurasian basin in the last decade or so, satellite images suggest that there's actually been something like 150% increase in primary productivity. So not only is the ice disappearing, but that region in the Arctic is becoming a lot greener. And that is consistent with the fact that more mixing is occurring. And we've actually got a second paper, which Kiki published in Geophysical Research Letters, I think about a month ago, which is actually looking at those nutrient fluxes and equating those with the primary productivity that is occurring in this region. And one point that it's worth making is, of course, that this mixing will mainly deliver enhanced primary productivity below the surface in what we call the subsurface chlorophyll maximum. So the plankton that have evolved to sit in the relatively low light levels at the bottom of the surface mixed layer to take advantage of this leakage of nutrients upwards. And so that's not actually detectable by satellite. So this enhanced mixing is actually really important within the Arctic Basin in terms of fluxing nutrients towards the surface from the main nutrient supply, which is the Atlantic and the Pacific Oceans. And the whole food chain is basically built on that. Now, I'm guessing what's happened in the Barents Sea is you've seen the spread of more mid-latitude species into that region, but don't quote me on that because, as I say, there's lots of papers by people that know far more about them that have just come out as part of the UK-German Changing Arctic Ocean program.
Right. So my second question is on the physics now. Let's go to the physics. And it's on the continental shelf waves you referred to.
Yeah.
And given the coastline configuration, have you seen any scattering of those waves? I would assume there will be scattering.
I would assume there would be as well, but we've never really looked at that data. So we were just focusing on explaining the dissipation profiles where that red dot is. So our focus has primarily been around 120 degrees east. There is a paper by Seth Danielson and the guys at Fairbanks, Alaska, which I think was also published in 2021, where they've done a sort of Arctic-wide look at continental shelf waves, but I don't think they've got as far as looking at the scattering off the coastline. You know, that level of detail really in the Arctic is not something that we've got to yet.
Okay, thanks, Tom.
So I see Bob Wilson online. Are you there, Bob? Or have you got you're hiding behind a letter W? I have a couple of general questions, Tom, without getting too political. Yeah. With this war going on between Russia and Ukraine, does that mean that, say, British ships or American ships cannot enter Russia's exclusive economic zone, which is 200 miles from their coast?
I don't think they could before. So the Russians have always been very protective, and they've got fleets of icebreakers, and basically you would have to get onto one of their icebreakers to go and make the measurements. So we've always gone with trips organized on the icebreakers by Igor Polyakov and the Fairbanks team. So 2 of our trips have been on Russian icebreakers in 2007 and 2008. But I mean, who knows what the situation is now with the current conflict.
And there's always been cooperation about sharing data once you're on board those ships.
No comment.
Okay, so another general question about this very powerful international research team. How did that come about? I mean, where was the nucleus of it? Was it you, or was it?
So within the UK, for the International Polar Year, the Research Council proposed a project which was ocean and sea ice. And that we were contacted by Sheldon Bacon, who's head of physics at the National Oceanography Centre, and also the late Seymour Laxon, who's a sea ice guy at UCL, asking us to become involved because they knew that we knew something about mixing and that nobody had been in the eastern parts of the Arctic where all the interest was making those sorts of mixing measurements. So that was how we became involved in the UK. And of course, all of the cruises are very much international cruises. So the first project that we were involved with, the two cruises, were actually run by Eagle Polycroft out of Alaska. And then through the next project, we actually got involved with the Canadians, because we were on one of the Canadian icebreakers, which is one of their coastal protection vessels, that was just doing a routine survey of the Canada Basin. So those measurements were made there. And then our last trip in 2013 was actually on the UK's James Clark Ross, which is not an icebreaker, it's just ice strengthened. But we were able to get within about 400 miles of the North Pole at that time because of the ice melting back. And that was actually predominantly atmospheric people looking at aerosols and cloud formation over the Arctic. But we managed to get space, and because they weren't too bothered about where they were making their measurements, we could go in the ocean where we wanted to go. So we were able to focus on the continental shelf break, because that's when we had an inkling that the tide was going to be quite important. But within the Arctic, there's so few people in the world that are working on it, on physical oceanography, that you very quickly get to know everybody. So, you know, if you want to talk about double diffusive convection and stuff, for example, you would go to Mary Louise Timmerman at Yale, because that's an area where she really knows, is the expert who's published the paper. So you would talk to her at a conference. And the German and the Norwegian connections are because our right-wing reactionary government might have taken us out of Europe, but as scientists, we still very much collaborate within Europe.
Interesting. A chat message just has come up from Robert Aller, who's a senior professor here. I have to run to a class. Wonderfully clear and integrated presentation. Thank you. And John, you're still there hovering around. Do you have a comment you'd like to add to this? You got involved in Arctic oceanography quite a few years ago. Oh, you're muted. Hold on. Well, you got to unmute yourself. There you go.
Okay, I'm unmuted now. Yes, I got really out of the shelf business about the time that Tom came in big time in the Arctic. So I haven't actually had direct input to any of the things that he's talking about. But I thought this was a very, very good exposition of where you've got to. I had a question for Tom, which is really about the relative importance of the two, as I see it, the two major mixing mechanisms that he talked about. There's the hydraulic control one, which seems to be driven by these continental shelf waves.
And the tide.
Background double diffusive convection, which is there sort of going on all the time in a very large proportion, I think, of the Arctic Ocean. And I just wondered if he had any comment to make on how you would assess the relative importance of these two. I mean, it's going to be one of the big issues if these are dominant, as you're suggesting, in their own particular ways. You've got one very continuous, almost steady system, and then one which is highly intermittent.
So yeah, Ilka Fur's done a back of the envelope calculation, which is in that one of the papers yeah, this paper here, where he actually shows that the unsteady lee wave mechanism linked to the tide fluxes about as much heat to the surface or into the surface mixed layer as the double diffusive convection does. So though it's over a much more limited regime, it's fluxing the heat up at a much higher rate. So it's able to, if you like, you've got one that puts a lot of heat up over a small area, which is the unsteady lee wave tide, and then you've got the double diffusion one. But I think the key thing about this continental shelf wave mechanism is it shows that any barotropic off-shelf flow has the potential to drive significant levels of mixing. And one of the things that's been observed to be happening in the last decade and a half or so in the Arctic is that the geostrophic circulation is increasing. So you might reach a situation whereby previously the situation just went over the bumps without there being any criticality in the flow, but it might just increase by 1 or 2 centimeters a second because we're talking about quite slow phase speeds here. And that's sufficient to all of a sudden put extra damping on the system and drive extra mixing. Because of course, it's not the tide, it's not the continental shelf wave that's causing the unsteady lee wave, it's that whatever the totality of the downslope flow is. So different processes are responsible in different places. Different processes are going to respond differently to climate change. And also you've got to remember the other side of that equation is stratification. So if you're changing stratification, which you clearly are in the Eastern Arctic by moving the warm water closer to the surface and also warming the warm water, or if you're doing something to change the salinity, then you're also changing that mechanism and the potential for that balance as well.
Tom, we have another question from Baoshan Chen. Can you hear me, Baoshan?
Yeah, I can hear you.
Yeah.
Hi, Tom. This is Baoshan. A very great talk. So I have a question about Atlantification in the Canada Basin. So as you just mentioned, and we have known that since the buffalo dry accumulates a lot of fresh water in the Canada Basin, so which makes the water column to be very stable, and the turbulence is very is minimized just in the subsurface water. But in the recent years, we also observed upwelling along the coastal line where the sea ice retreats to the basin area. So and it's also to be more and more frequent for the wind-induced upwelling along the ice edge. So my question is, if upwelling will affect the heat exchange between the Atlantic water and the Pacific water, so just the heat exchange between these two water masses and bring the heat to the surface to just help the melt of more sea ice. But another question is, since the Atlantic water is warmer than the Pacific water, so if heat can be brought to the surface and the surface salinity is still low, so it means the stratification might be stronger. So I would like to know the feedbacks between this heat exchange and the sea ice melt in the Canada Basin. Thank you.
So, I mean, I've only talked about vertical exchange processes, and one of the important mechanisms for getting heat into the Canada Basin, the melt ice, of course, is eddy motions, and they seem to be changing. So I'll point you at the review article I mentioned there, because that's really neatly written about by F.E. Fines from Woods Hole. The other issue, it's not just the heat in the Atlantic water, it's what's happening to the halocline above it. And I think Mary Louise Timmons had a paper last year or the year before where she actually showed that the heat content in the halocline was rising quite rapidly. And that's actually linked to the fact that you're getting much more mixing on the continental shelf as the sea ice retreats. So it could well be you're changing the stratification, not only by piling the fresh water up in the Beaufort Gyre, which is occurring, but also by changing the temperature. I know the temperature has a much smaller effect because you're quite close to the freezing point, but that is an effect that needs to be thought about, and it needs to be properly accounted for in models. Now, the whole shelf break thing, obviously the continental shelf waves are going to be important. You do get some enhanced tidal mixing. I think, I can't remember what the exact name of the region, but that around the Chukchi Sea sort of area as well. So you do get some tidal mixing there, but again, upwelling mechanisms could be important, but they're constrained to the topography region, aren't they? So in terms of thinking about the future, where the sea ice is going to disappear completely in the summer, I think an important point to make is that all of this enhanced mixing appears to be limited to where there's sloping topography. And okay, the ice moves around, but if all of the heat's going up in certain places, then we can't just apply a uniform heat flux, which is what people appear to be doing. to get to an assumption that the sea ice will actually disappear completely in the summer by 2040 or 2050 or whatever. And it means that all of these processes, the eddying, the upwelling, the tides, they all need to be parameterized in these global climate models if they're going to be able to predict the sea ice retreat with any sort of skill.
Yeah, another thing is that since the buffalo gyre was expected to be weakening in the recent years, but it's still strong. So if the buffalo gyre is getting weakened, so most of the fresh water can be exported through the Canadian archipelago to the Atlantic Ocean. So it means the stratification will be weakened and the turbulent mixing may be strong. So do you think the Canada Basin will be the same as Buffalo Sea in the future, with the turbulent very prominent in the subsurface water and no sea ice in the summer?
I think the key point about the Canada Basin is you're relying on wind energy, and there's a severe limitation because of the high latitude on the penetration of inertial waves. So I think there was a paper last year which showed that they're 6 times less effective at high latitude than they are at mid latitude. So it's not only the tidal energy conversion, which is severely constrained by the high latitude, but also the effective inertial oscillations in radiating inertial waves to depth to provide the shear to drive the mixing. So even if you're reducing the stratification, it depends. I mean, if you can manage to bring the Atlantic water up to 100 meters or something, you can probably get the same situation as you get in the Eastern Eurasian Basin. But I'm guessing the whole point is, so you think about the Barents Sea, you're losing all this heat to the atmosphere all year round now, which is much more than you used to. That means that heat isn't getting into the Eastern Eurasian Basin. That means that less heat's getting into the Canada Basin. So what all of these different processes interacting in these different locations are actually going to change the availability of the heat getting to different locations as well, which is why we've got to get all of these processes working in models to really get the understanding of how that works.
Okay, thank you.
So you're muted now, Malcolm.
Okay, I'm sorry. Are there any more questions? If not, Tom, we'll close it down. I've been kicked off the internet, but I'm back. So I just want to thank you very much for giving up your precious time to present us today. And the significance of it is very profound.